What's up guys, this is Andrew, your computer science teacher for today, and in this video we will implement the fast modular exponentiation. So open your code box, stick with me and let's write this code together. I will create a new project, console application, C++, and it's going to be called fast modular exponentiation. Perfect, hit finish. Now go to the source and let's delete this hello world. Alright, now as we've seen, we will have a function, and this function is going to be returning an integer. So int is going to be called fastexpo, and is going to have three parameters, which are the variable n, its power, which is going to be a long because it can be quite big, and the modulo, right? So int mod. Perfect. So we want the remainder of this expression. Basically, let's free slash so it can be seen better. So by the way, if you didn't know, this is a comment. You can comment using 2 or 3 slashes. So we want basically this expression a at power n to be computed modulo mod, right? Now there are two possible ways of implementing this algorithm, and those are recursively and iteratively, but each one of them has its main advantages and disadvantages. We will write both of them, but first let's break the advantages and disadvantages of each one. Now the recursive function is way cleaner, so the code is simpler and cleaner and even safer, but the main disadvantage with this is that when defining recursive functions, which basically call itself inside itself each time, right? The stack has to retain a lot of memory. So for each call of that function, let's say for this function fastexpo, we know three parameters, right? It's a, it's n, and it's modulo. So let's say we call this function with a equals 2, n is 100, and modulo is, I don't know, 13, right? Inside this function call, we will call this function another time with 2, 50, and 13. Then another time with 2, 25, and 13, right? And so on. Now, the stack has to retain all this information. It has to know that after performing this function call, 2, 25, 13, finishing this function call and knowing the result, it should return to its original parent, which is this function called 2, 50, and 13, right? So it should store on the stack all the function calls, or the recursion tree as we like to call it, right? Because the recursion tree, it has nodes, and each node is a function call of this type, and it has sons, basically the function calls inside that function call, and so on and so on. So you can imagine that that tree can get quite large fast, right? Now, if you can write the code in an iterative manner, and it doesn't get too ugly, and it's pretty easy and safe, I recommend you do that because of this stack problem, right? If you can't, it's okay to do it recursively. We will see that in a lot of problems, we will prefer the recursive manner. So let's write this first example, which is going to be the iterative implementation. So first of all, I will define my variable ans, which is going to store the final answer and is initially obviously equal to 1. And I want to show you practical examples to understand better what our algorithm is going to perform here. So an example is going to be, let's say I'm going to have a equals 2 and n equals 13, right? So I basically want to compute this expression, 2 at power 13. And initially, my answer is going to be equal to 1. So I take a look at the first step. And at the first step, I notice that n is now an odd number, right? So n is odd. Because n is odd, what I'm going to do here, in order to compute 2 at power 13, this expression could be written at 2 crossed 2 at power 12, right? So what I want to do here is, I want to make answer to be equal to this 2, right? So I don't have this 2 anymore. I transported it to my answer, and now I will have to multiply my answer with 2 at power 12. So instead of 2 at power 13, I remember with 2 at power 12, right? So in order to do this, what does it mean? It means that a is still equal to 2, but n is now equal to 12. So after the first step, a remains 2 n is now 12, so it decremented, and answer is now 2. Now, at the second step, what it happens here? Well, I see that n is an even number. And because n is an even number, this expression could now be written as 2 at power 2, all of it at power 6, right? So at power 6. So now, instead of multiplying 2 12 times to my answer, I will have to multiply this 4 6 times to my answer. So my a is going to be equal to 4 now, n is going to be equal to 6, and answer is still going to be equal to 2, right? So by now I have in answer only the value 2, and I know that in order to get the final answer, I need to multiply this value 4 only 6 times, right? Let's take a look at the third step. Now at step 3, I see that n is still even. If n is even, that means that this expression, which is now 4 at power 6, could be actually written as 4 at power 2, all of this at power 3, right? So now, to my answer, I will need to multiply 3 times the value 4 squared, which is 16. So a is going to be equal to 16, n is now going to be equal to 3, and answer is still equal to 2, which is perfect. Now, at step 4, I take a look at n and I see that is odd. So n is odd. And what does it mean? It means that this expression, 16 at power 3, could actually be written as 16 crossed 16 squared. So now, if n is odd, a remains the same, right? N decrements itself, so remains equal to 2, and answer, I'm going to transfer this 16 into my answer. So answer is now 2 cross 16, which is 32, right? Now, at the fifth step, I see that n is even again. Now, this expression, 16 at power 2, could be actually written as 256 at power 1. So a becomes 256, n is equal to 1, and answer is still equal to 32. And now the final step, which is step 6, is that n is odd. So this value, 256, could be actually written as 256 crossed 256 at power 0, which is obviously 1. So now a is going to be equal to 256, n is going to decrement itself, so it's going to be equal to 0, and this time this 256 is going to be transported to my answer. So answer is going to be 32 crossed 256. Obviously, I don't know the math for that, so I'm just going to compute it. 32 256, which is 8,192. So this big value, right? And now n is equal to 0, so our program comes to an end, right? So this is basically how the iterative version works. Now, let's put this into code. So as we said, we will have a while loop. Obviously, as long as n is greater or equal than 1. And if this happens, we will have our analysis, if n is odd or is even. So we need an if statement for that. Now, if n is odd, so n modulo 2 is equal to 0, what will we do here? Well, we see that a becomes a squared. N becomes n divided by 2, and answer is still the same. So I will basically have a is going to be equal to a crossed a. Don't forget the modulo mod. And this is getting tricky because this product could be actually quite large. We will perform a trick, and the trick is we will put 1 LL here because when we have the product of some variables or some numbers, the type of the product is going to be equal to the type of the largest variable or number. So if we only had a crossed a, this a is an integer, and if let's say is a pretty big one, like 10 at power 9, this product is going to overflow the integer upper bound. So we need a long for that. But now, because we have 1 LL, which is the number 1, explicitly converted to the type long long, we know that this final product is going to have the type long long. So even if it's big, it fits into the long long type, and then we have modulo mod, which is going to make this product again an integer, and it's going to be stored in the variable a. And as we've seen, n is going to be divided by 2. And that's it. Now, if n is an odd number, so else, what we have done here? Well, basically, each time n is odd, we have taken 1a from this expression, right? We have taken 1a and transferred to the answer. A remains the same and n is decremented. So, answer is going to be, again, 1ll crossed answer crossed a modulo mod, and n is going to be decremented. And that's it, guys. After this while loop finishes and I'm at n equals 0, this was the final step, so I will return my answer. And this is the iterative version, guys. Now let's go into int main and test it a little bit. Let's print, let's say, fast expo of 2 at power 10, and the remainder, let's say, I know this is a quite large prime number. It's going to be 10 at power 9 plus 7. So this is the number, right? So I need to have 1024. Let's see. 1024. This is perfect. Now, let's try another one. Let's try, I don't actually really know large powers, but let's try 7 at power 10, let's say. All right, 7 at power 10. And it's going to be that number. Obviously, I don't know the result to that. So let's test it with our amazing calculator. So we will have 7 at power 10, which is going to be this number, and we are going to have it 282475249, which is perfect. Right. So it works. Now a corner case will also obviously be power 0. 7 at power 0 is 1, which is quite great. So we know that our function works. Okay, guys, this was the iterative version. I really hope that you understood it and enjoyed it. And now let's get to the recursive one.